Okay, so our final talk of this evening and also of this conference is by Roelof Pieters from 23 AI, as we can see on the screen. Be sure to stay tuned after the talk for a bit, because then we'll have the closing notes from our two from Matthijs and Marisha. I'm having a little bit of blackout here. So be sure to stay tuned after the Roelof talk. And well, I'm very curious to hear about how you watch millions of trees with Python and what kind of impact you can make with that. I would say the floor is yours. If you have your screen to share, you should be able to do that as well.
Great. Yes. Can everybody see this?
I think so. It looks good. And the floor is yours.
Great. So good evening, everyone. I'll try to make this quick and snappy. I'll try to stick to 30 minutes since I understand I'm the last one of the conference and there's some other nice things going on after me. So I'm Roelof. I'm the CTO of 23, where we build kind of technology to look after the planet, mainly trees and other vegetation. And we do this continuously all over the world, and mainly to take action against climate change and as well make better decisions about our shared environment. So I'll start telling a little bit about the problem we're trying to solve, or at least have some impact on with 23. Then I'll talk a little bit about the specific domain of satellite imagery and how we work with it, and also what role Python can play in it. And then also show some examples of some of the stuff we're doing, as well as a little bit of our own ongoing research. And also, if you are so inclined to work in this domain yourself, which I hope some of you will be after this talk, giving some pointers to like where you might want to look first. So I'm very fortunate to be part of an amazing team. We're around 7 now. We started 2 years ago. And as you can see, we have a quite strong data science focus. We mainly work with large corporates, NGOs, since we kind of believe those are the kind of entities that have the largest impact on the client, on the climate and on the planet, for better or for worse, and where we also want to kind of steer things in the right direction. So about me, very shortly, I started out as a computer scientist at the University of Amsterdam. Then I moved for 10 years plus to social science, more specifically anthropology, and found my way back to software development. I used to be based in Sweden for 10 years plus, where I worked for a couple of AI startups and also started a startup. And then when I moved back to Amsterdam, I joined 23, but I've been there now for 6 months. So on to the real stuff. And bear with me, this will be kind of 5 minutes of bad, like the bad stuff that's going on. And then there will be 25 minutes of like, what is the amazing stuff we can do about it. So there's 5 minutes of doom and then 25 minutes of positivity. So I would start like talking about how amazingly beautiful forests and trees are. But let me just say that like keeping forest intact is literally like a prerequisite for our own survival as a species. As we all know, our planet is under pressure. Previous speaker already talked about deforestation, forest fires as well, which are increasing together with kind of extreme climate events. And so these have really a large impact kind of on the society as well as our economy. And so, yeah, we believe that kind of we really should try to halt this as much as we can. And so forests already have the size they once were. And ongoing deforestation, which is a nice word for destroying entire ecologies, emits about 15% of global greenhouse gas emissions, which is quite large as a portion. So why are forests so important? Well, first, forests create oxygen we breathe. They're also one of the major sources of our food and water. They regulate the hydrological cycle, which basically is a fancy word for saying they produce the rain we need for our crops. And also they are kind of the largest diverse biome we have that give like life to about 80% of all the non-human life on land. So that's a quite important part of our planet to kind of keep intact. And so at 23, we think that one way to try to tackle this issue is that we need more data-driven information, which then can help like making better decisions about our natural resources, as well as more transparency. And so by applying machine learning to high-resolution satellite imagery, we essentially create what we call then planet intelligence, which are insights into both the quantity and the quality of our natural resources. And so some last maps about what's going on before we go into more detail. Here you can see like our current forest in dark green, and then the more semi-forest in light green. And you can see they cover quite a large portion of our total landmass. And the actual forests cover around 20% of our total land. So if with 23, we always say like we work with forest, and that can seem quite niche, but like if you imagine that that's 20% of the land, that's still quite a large portion of the world. And this is actually what you can then see through our friends at Global Forest Watch, if you want to learn more, what is going on with deforestation, which is going quite rapidly. And it's something like I strongly believe that technology is kind of one really important piece of the puzzle, but it's not like sufficiently enough. And this is a book I really recommend anyone working in technology to read, Seeing Like a State by James Scott. And it's essentially about simplification and standardization. Like when we create big systems, as many of our like software developers do, we like to create systems that have some effect in the real world. Often there's all kind of unintended consequences, which we could have actually thought about a little bit better beforehand. And so one example that's quite relevant here, I'll skip the quite large quote. It's like, this part is the important part. It's, I think Vincent earlier talked about like active empathy. And it's essentially, it's about like active listening, right? So it's about, as technologists, we like to always jump into problem solving mode, but this is about like trying to take the time to understand our users and problems first. So a little bit more design thinking approach. And this specific example is about the rise and the fall of German scientific forestry, like relevant to the story I talk about in the late 18th century, where like a lot of forestry and forest companies thought, okay, like trees are quite wild and these ecologies, like they're really not manageable. We should be able to do this more scientifically and more standardized. And so essentially what started to be done is we like foresters turned, which we have a lot of in Holland to the right. You can see this nicely planned forests. But essentially, initially it worked really well. Like forests started producing more timber, and it was especially more manageable and more measurable. But already quite soon after like another forest cycle, like trees essentially started dying out. And you had this concept of Waldsterben, what started to come around in the German-speaking world. So just to say, like sometimes like the cure is worse than like what's going on. So we should be quite careful, like when we put kind of quite powerful technologies into the world and really think about it, but also especially get the people who we're supposed to help as much involved as possible, as early as possible. So almost at the end of the drama story, forest fires, another major contributor to climate change, which I will go a little bit more in detail in. They're on the rise. They have a large impact on greenhouse gases. Like simply said, like trees killed by fires will decompose and release carbon. They will also not be existing anymore, so will not be sequestering carbon either. Fortunately, this looks quite horrifying, but a big part of this is also part of a natural cycle of burn and recovering, except maybe in like the US and Australia and Russia, not so much, and Amazon. But it doesn't look like as nasty as you see here. Still, it's a process we want to halt as much as we can where it's needed. So for the good news then, what can we do about it? Well, first of all, tracking fires from space, as you could see before, it's actually pretty straightforward. We can identify trends quite well. They're pretty massive, and so we can see them actually from satellite imagery at like 800 kilometers away. Here you can see an image from the Copernicus installation from the European Commission from California in 2018. And since they're like satellites have many different instruments, we can also look at different bands, like multispectral imagery, as you see here. And this allows us even to look through these clouds. Like here, you can't really see what's going on, but using this kind of more multispectral data, we can look through the clouds and really see more of the scale of the fire. So that's all nice and good. And we can, of course, analyze this automatically. But we don't really want to track wildfires only. We want to also prevent them. So with 23, around a year ago, we really started looking at like the main causes of forest fires. And so we found out, like just one example of like a use case, we found out that power lines, surprisingly, are actually one of the main causes of forest fires. And this is more specifically because of the interaction of overhead power lines with trees. And just in California, for instance, like there was this massive fire, which was caused by 40% of the area burned was actually caused by just power lines interacting with trees, like trees falling down on power lines or like storm or things like this. And so that's a huge problem. And it should also be quite a solvable problem. So what then about satellite data? What can satellite data do to help? So let's take a step back. And also what makes it possible to especially now, have such a large impact that we can really like bring this to a halt. So what has been changing in recent years is that the number of satellites being launched is really, really increasing. So that's essentially what you can see. And with the number of satellites, also the number of instruments and also the price. So here you see the different launches going on in last week, actually. And this means also that the price of being able to hitch a ride on one of these launches and put your satellites there, together with the size of satellites going down. So from the size of a bus, like a double-decker bus, to kind of the size of a little, something that fits in your hand, almost, these CubeSats. You can essentially like quite cheaply get your satellites into the space and then use it for good. We don't do that ourselves, but we have a lot of partners we work with. So here's an example of the kind of imagery we look at. So here you can see 30 centimeter resolution. You can see quite a lot of things from the tree level, human eye. But this is are the three RGB channels. So that's quite usual, like what we're used to see. But there's many other spectrums. We have what we saw earlier, the multispectral range, which is used for understanding the health of vegetation. So here you can see all those different spectrums. But we also see other things like radar imagery, which is useful to look through clouds and also at nighttime. So even if there's clouds, like at rainforests are generally quite cloudy, we can actually look through the clouds or when there's no light. Other things that are kind of feasible within kind of the last few years is that there's many more companies available that have their satellites that allow us to do quick revisits. So we can like really from day to day see how particular places on the planet are kind of changing, which you can see here. And finally, like different resolutions. So here you can see the harbor of Rotterdam. So a 2.5 meter resolution. So quite blurry. You can see some things, but then this is the difference you get with like more commercial like data available from 2.5 centimeter. So you can even identify the individual containers or cars and things like this. So this also helps us then to label things much better. So what we've been doing over the past 2 years then is basically that we have a lot of data from our partners we work with. It can be things like infested trees, of which we have more than 100,000 trees around the world, where we know the exact coordinates and the times, but also climate data and whatnot. And on the other hand, we have petabytes of unlabeled satellite imagery. So there's a big unbalance in a sense, like we really have like normal computer vision problems. There's always an imbalance, but this is like an extreme imbalance, right? So what that can be, like, what does this data then consist of? Like, first of all, when we look at satellite data, we want to look at the location, like where do we want to get an image from, the time, what is the date? And then we want to look at things like what portion of an image is covered by clouds, like maybe we want to find only images that have less than 5% covered by clouds. And then we see, of course, if they're available or not. And then we have to do all kind of post-processing steps, since there's a lot of noise in satellite data generally. Do some other stuff, train a model, and win. So this is essentially how this looks like. Here we have the Sentinel constellation, which is a 10-meter resolution. And just to kind of compare with kind of normal computer vision problems, like just if we would take, like here we have Holland, we have like 3 tiles or images make up like the entirety of Holland. Just if we were to take like Holland, and we would take like 1 image a day for an entire year, we already have data that's about 3 times the largest open computer vision data set in the world, like open images. So this means we really like have a lot of data to work with. And what you can see here is like our internal repository. So here you can see to the left, you can see us loading in some kind of trying to query some satellite data with like some simple line of Python code, so we can identify it by tiles. We can see the cloud cover, etc. And on the right, we can do the same by specifying a particular area of interest. So that's quite useful. Then, of course, once we have that image, and you can yourself download these things easily, like Sentinel 10-meter resolution is freely accessible for anyone. But then we want to, of course, download it, and then we can plot it and see how this image actually looks like. So that's great. That's a quite relatively easy way, like there's the post-processing step missing, but it's a relatively easy way of actually acquiring satellite data and images of the world. So anyone can do this, like for particular problems you're interested in. And that's quite useful. So what then we do with this data? Like how do we make models that we can do this for the entire world? This simplified technical pipeline, I won't really go into much detail, but we have like different providers you can get data from. We have our own data pipeline. We have a model zoo where we have like different models we're training and different versions. And then that makes it up into like a dashboard, which we sell as a subscription service for our clients and an API. A lot of that is like powered by Python, quite simple Python code. And so the kind of techniques we then use is, on the one hand, we have top left lens segmentation, which is like the more standard stuff. Anyone working with machine learning knows the kind of UNet approach. So you have like an autoencoder type or like residual connections. So we create segmentations of like, let's say, stuff like land cover, which means if particular areas are like forest, or if they're urban, or if they're water. Then we can also put that into what you see bottom left, into like an LSTM or a transformer, like the kind of stuff Raza and Vincent loves to play with, like the transformer stuff. And so we can create like time series things. We can do like a change detection. Other things we can do, top right, is more the classical computer vision stuff, where you do bounding boxes and we can count things. And then because we have so much unlabeled data, and partly what I did a lot of my PhD work on was on unsupervised models. So we can do unsupervised learning, semi-supervised or self-supervised, like there's different ways of doing that. But essentially what you can do is like you take an image which you don't know anything about, but you can turn it into data by just doing something smart with it. Where in this case, like intuitively, you can just say, like, which of these pieces, A, B, or C, is the kind of missing puzzle piece which you would fit into here. And clearly that would be B. And that's a nice, learning task you could create from any kind of data. And that lets you create like really nice representations of data without needing any labels. And this allows us to kind of work with like 2 factors less data, or labels, I should say, which is quite useful since essentially getting labels can be quite costly. I'll try to speed up a little bit so I can reach my end time on time. Other things we do is stereo imaging. So we take like multiple images from different angles from the same place and projecting these onto each other, we can create 3D maps. And so we can do things like the heights of trees or cities up to accuracy below 1 meter. This is kind of some smarter approaches if you're really interested in do that. The link is there. It's kind of a way how you can do SIFT type features, but you can do it neural network style with some graph convolutional nets in the middle. So that's a nice paper. We do things like with my previous failed startup, Creative AI, did a lot with like generative models. So we can take freely accessible data on the top right, and we can try to transform it into commercial data. And this is not a real example, like this is too perfect, but it's the idea that you can turn the top image into the bottom image with some generative models, essentially like the GAN type models or whatever you want to use for it. And so how we do this, we use like one of these models, also freely accessible as code in PyTorch. And we try to see this as a time series problem, where we try to upsample different resolution imagery with every time step a little bit. So 2 times up to the level where we want it. And from that, we actually get imagery like this. So we get like the left image, which is very blurry and straight from the satellite. And we can upscale it to something where we can actually see more clearly what it is, and also especially label it. So we can see, okay, this is clearly, there's on the top, there's a palm there together with some other kind of bushes and some other palms to the right. So that's quite useful. Other examples where you see houses that are a bit more clearly identifiable and roads. And so what allows us that to do is like do less with more, right? Which would say, and that's quite important because we, in our case, like creating labels from, let's say, a tree that is distressed or sick can be like a 2-day hike right into the middle of nowhere. So we want to limit this as much as possible. Or when we ask our customers or partners we work with to do that for us, or people we hire in the field, it really has to have the largest impact possible. So for that, we use active learning, which essentially is a way you have training data, you have your machine learning model that you train on it, then you have some unlabeled data, which you do run inference on, and through some Bayesian learning or whatever you want to use it, you can try to find the examples that not just purely random, but you can estimate what the neural network knows the least about and try or have the most impact on the training regime, and then ask human annotators to label that essentially. And so that's what you can see here is example, another library which you can freely use and play with from friends of ours with Element AI. We also do a lot of interesting stuff with satellite imagery. So there you can do like Bayesian inference type stuff, which means you just run a trained model multiple times and you just add dropout everywhere, and you essentially approximate like a Bayesian neural net without much, without much work. Not super efficient, but it works, and you can get nice probability estimations of uncertainty. So that's what you can see here. You have to the left, you have some predictions of trees, like sick trees in this example, and it's zoomed out heavily, so there's a very large plot of land. And then to the right, you can't really see it well, but here I put the arrows, you can see little red dots. That's the top 5 or KN, whatever clustered top most uncertain parts. And then we can ask people to specifically go there, or if we can see it ourselves on the satellite imagery, if it's like high resolution, we label that and we add it into the mix, and we can kind of read through and label that again. So machine learning, we use fastai, very high level, lets us experiment rapidly and easily. We do PyTorch as well, which is a bit lower level. And we have a repository, setData, might be renamed. And once kind of the main bugs and stuff, and it works smoothly, are worked out, we actually would love to release this publicly, allowing anyone to kind of apply fast AI style, easy to use neural network code with just a few lines, being able to use satellite data for hopefully good things. And why we love this is because it's like layered. Everything is customizable, pluggable. It has a lot of best practices in there. So it just has like really good standards. And we try to follow this for satellite imagery as well, which is like, it's quite tricky. But that's the idea. So that even with limited knowledge of satellite data, you should be able to come in and do a lot of like useful things with it. Then other things that are great, there's the link for people who don't know it. It has like custom transformations and easy two-way callbacks. So we can put all kinds of like callbacks on it. Instead of having to change code, we can essentially patch functions, and we can just override it with type annotations or whatnot. Example here is, for instance, a get data loader. It's essentially, it goes onto the PyTorch normal data loader, and you see here after batch train, after batch valid, and you see some custom transforms. So we want the training part of the data set, we want to have some augmentation, and the valid, we don't want this. And then we have some other stuff on there. And this is then how we can use it. So we have all kind of other custom callbacks here. So we have filter predicate, which lets us filter images if there's no data or if there's a lot of nonce. We can do all kind of after item stuff as well, which is a way where we can just do extra transformations. And that's a quite useful way of like overriding existing functions without too much work. And here you see how this then looks like with more the standard fastai type code. So that's quite useful. Other things we can do is what you see here. This is from the standard fastai documentation. You can do custom type annotations and also, for instance, this kind called named types, like named tensors. And through type dispatch, which is what you see here, you can essentially have the same function, flip all R, flip left, right. But you don't really have to worry if you use it, like what your particular type is. So you have, instead of having to rename or do all kind of like if then else statements about what the type is in type checking, you can just create different functions with the type annotation, and it will just run that function if your if it's the correct type. So an image will have different transformations than, for instance, a bounding box, right? So that's what you can see at the bottom. You can just do whatever your type of data point is, and you just do flip left right, and you don't have to worry like what is the type, and it just works. Other examples here, I'll skip this one, but here in some of our code ourselves, you have a transformation. So there's a custom transformation which encodes data. So it does some, let's say, augmentation encode. And it also changes the type. So it turns the seg map into a transformed seg map. And then we have a simple decode, which is automatically run when we do the transform backwards. And it just checks if it's a transferred seg map, it will decode it. But if it's not a transferred seg map, then it will not decode it. So that's another nice way of using kind of type annotations to make things easier. Serialization is quite useful. I'll skip this example, but it's if you don't know DIL, try checking it out. It allows you to essentially also pickle entire classes and functions within your dumps. So the problem is if you would run this, you would have function pointers, and your functions wouldn't be pickled, only the links to the functions. But in our case, we have all kinds of custom functions. We just want to package up into the model definition automatically when we export it, so people can use it. And that's essentially what you then can see here. I'll skip the code, but it's essentially just a way of being able to wrap all of that up. Even if functions don't exist or you don't have access to that, they will just be picked up within the model definition. So I'm aware I only have 5 minutes, so I'll go a little bit faster. I'll skip this part. This is just what are kind of best practices for debugging. Basically, when you debug your models, we learned the hard way to always make it easy to inspect things visually, which I think is underappreciated. So we always like to look at top losses, but here, for instance, we automatically plot augmentations, and we can see just sanity check things visually a lot. Other things we do is we can automatically inspect model uncertainties. So to the top of it, you see actually the uncertainty map. You can see which models are more certain than the others. The bottom, you see like a histogram plot. So you see that the right model, these are 3 models kind of in the vertical axis. So you see that the all right model has a more normal distribution, which means it's more spread out and better trained, more generalizable, which you can also see in the predictions. They're a bit more robust. Other things you can do once you have uncertainty estimates of models also per classes, you can, instead of this, when you would kind of merge these predictions as an ensemble, you could also take the uncertainty predictions when you argmax things, and you can take that into account that you get much more accurate predictions. You can use it to debug things, class probabilities, and then I'll skip a lot of the rest, which basically means inspect things visually because metrics don't always tell the truth. nbdev is what we're using, which we wrote a blog post about, which you can read yourself on our Medium channel. But basically how we use it, it's a way where you get like IPython notebooks with all the benefits of a normal IDE. So here you see repository where we essentially have IPython notebooks. Some people might hate notebooks. They're messy. They're only good for experiments. We embrace it. So it means we can iterate quite quickly with them. For my notebooks, we automatically create libraries. So these are full Python packages. So it's the same stuff. And we can do this through all kind of annotations. So you see the export annotation here, which means that these functions will automatically be turned into library functions, with the benefit that once we compile it and push it to GitHub, things are actually automatically compiled into documentation as well. So here we have automatically Heroku documentation created, and we have even things like interactive maps and stuff are all automatically correctly created. So that's quite useful. And then other things which nbdev, which is from the makers of fastai, also allows you to do is kind of do proper CI/CD stuff. So you have through GitHub Actions, you can still do certs and all kinds of tests in your notebooks, with the benefit that you don't only have just tests in your notebooks, but you also have all the documentation and easy readable stuff in there. So instead of working more like this would be the usual thing where research and experimental might be some more notebook type stuff and the production is more libraries and separate code, we really embrace it and we get more agile type software development. And so we use libraries like this for this. Most of them I covered already. MLflow for experiment tracking and models. And then we use Redis as a high throughput I/O a database mainly for large-scale inference, when we have to kind of take a map of the world, have to package it into smaller patches we can predict on, and do all kinds of fancy stuff with it, and then put it back, like get it all aggregated back into a map of the world. And so there's all kind of bottlenecks, CPU, GPU, memory-wise. And so it's kind of modularized event task management system, and it makes use of Redis. So Kubernetes or all these kind of things would be nice if you have like individual images. But if your image is essentially one large image, this is we found a little bit better approach. So final use case then, I'll skip the example. It's basically this preventing forest fires by overhead power lines. We essentially just have this different input tiles. We have our kind of models that create a vegetation map. And then we have other models that do power line inspection. And we create this dashboard, which is a product we actually have for utility clients, which can do all these things. It can get hotspots. It can do all kinds of other things. And that's it. I'll skip the rest. It basically just shows a little bit more if you want to get started yourself, but that will be in the slides. So it's just like if you want to get started with some easy library, there's EOLearn. There is Google Earth Engine, which lets you do kind of simple remote sensing stuff in your browser. There is other things that are useful. There are data sets available. So all these links will be in the slides. There's some other resources, way too much to cover. But if you want to get started with some code or some tutorials, then there is a nice paper. If you want to really get started with more the AI approach to climate change, this is a kind of nice introductionary paper which covers a lot of different problem sets and what are kind of techniques that might be useful for it. Also available at climatechange.ai. Then if you're a software developer, you just want to build websites and do a lot of other useful stuff, not necessarily as data sciencey. There's climateaction.tech, also a Slack group where a lot of us are hanging out and helping each other and trying to come up with good things. We have, you can go to bit.ly 23AI, where you can see a kind of a Twitter feed of some of the stuff and some of the news that's going on with 23. But essentially, we're hiring. We're looking for more people to join the team. If you want to do your own startup, since I'm very much in the startup space, there's 3 new funds just launched last week or this week. It's pretty crazy. Pale Blue Dot, actually, also which we'll be launching as an investor. We'll be announcing that quite soon for our seed round, but also Prime and Lower Carbon Capital. So there's a lot of climate-related impact funds that are there. So if you want to run your own startup and do some of this stuff, the best time is now. And that's it. So not sure if we have time still for questions, but I can always see you on Discord.
Well, thank you for this interesting talk with a very clear mission and also, a nice technical overview of the way you approach these. I see 2 questions. I think we have time for them before we go to the closing notes. So the first one by Core is the question whether you use a CNN to create the point cloud or do you use more classical CV techniques?
We use both. For some baseline, we always like to do classical remote sensing as a baseline because there's no point to do fancy models if it doesn't improve things. And mostly that's related to data. So neural networks, deep learning are great, but there needs to be a kind of a data requirement that fits that complexity. And so we use both. We use dense convolutional mapping. It's pretty standard these days. But yeah, there's a lot of extra fans. So what we're looking at more is multitask learning. So I covered a little bit about the kind of embedding techniques we're using. So the idea is that we have specialized small tasks with our heads on a larger model. And so we can have specialized training data, but still get the benefit of combining all that data together with specialized training regimes. Check out the stuff by Andrei Karpati for Tesla. If you want to know more about that, they're kind of, I think, state of the art in multi-task learning.
All right. Then another question by Karsten. He says, monitoring deforestation is sort of like writing tests. It's only useful if people pay attention to it. So how do we get it to lead to actual decrease in deforestation activity? Any thoughts?
That's with everything. So that's actually a big challenge for me when I really wanted to do something impact-wise with AI, and why actually for a long time I didn't do much AI. I actually moved away from AI for a year, doing hardware stuff, because I felt that that's where I could have an impact on the ground. Because yeah, you're right, like AI is just a tool, and then the tool has still to be used. Like it's great that you can see where deforestation is going on, but then that still has to be transferred into actual action. And so for that, we work with partners, like we work with large NGOs and large corporates that essentially do these things, but they do it very manually. And then we just help them do that more efficiently and at scale. But that's right, like you should start from the problem and the actual challenge, and not so much from, creating nice virtual technical models of things, which might look good, but don't as such bring any change.